You're sitting beneath 11,000 tons of steel right now, and it's about to move. That's heavier than the Eiffel Tower and 3 fully loaded cargo ships combined. In 20 minutes, this entire structure will slide open or shut directly above your head. How does something this heavy move without crushing its own track system? How do engineers keep 50,000 fans safe beneath a structure that weighs more than most bridges? What happens if a single motor fails mid-motion, with the panels halfway open and a storm rolling in? The answer borrows technology from battleships, offshore oil platforms, and NASA spacecraft stabilization systems. And once you understand what's actually holding this thing together above you, you'll never sit under a retractable roof the same way again. Let's start with the raw numbers, because the scale alone is enough to stop most engineers cold. The first true retractable stadium roof opened in Toronto in 1989 at what's now called Rogers Centre. It weighed 11,000 tons. That's heavier than 30 fully loaded Boeing 747 aircraft, all suspended above a single building simultaneously. Modern versions have grown dramatically larger. Some retractable roofs now span over 220 meters in diameter, wider than 2 Olympic swimming pools placed end to end, with room left over. The total roof surface area on the largest modern systems exceeds 25,000 square meters. To visualize that, 4 full-sized football fields, laid side by side, all covered by a single moving structure. The steel framework alone on some systems weighs over 14,000 tons. For comparison, the Golden Gate Bridge contains roughly 83,000 tons of steel total, meaning some stadium roofs contain nearly 1/6 the steel of one of America's most famous landmarks, all designed to move on command. Construction costs for a single retractable roof system regularly exceed $300 million. Some projects cross $500 million. That figure alone could build 4 professional soccer stadiums from scratch in smaller markets worldwide. Full roof operations typically complete in 10 to 20 minutes. Traditional construction cranes moving equivalent steel tonnage would need days, sometimes an entire week, to accomplish the same task manually. Individual roof panels can weigh up to 600 tons each. That's roughly the combined weight of 3 Boeing 737 aircraft, all balanced on a single rail system and moving at controlled speed. Operating speeds rarely exceed 2 miles per hour, slower than an average person walking a casual pace down the street. Wind tolerance thresholds are typically set around 45 miles per hour before automatic lockout systems engage. But the structural engineering goes far beyond that. Some roof systems are rated to withstand gusts exceeding 100 miles per hour while fully open. That's equivalent to Category 2 hurricane force, hitting a structure that's actively mid-motion. These aren't small mechanical systems with generous tolerances. These are structures carrying the mass of small steel bridges, engineered to move with the precision of a surgical instrument and the reliability of a commercial aircraft. Every single number here represents an engineering constraint somebody had to solve from scratch. So how does something this heavy actually move? The answer surprises almost everyone who hears it for the first time. It doesn't lift, it slides. Picture 2 massive steel panels, each roughly the size of a football field, approximately 100 meters long and 70 meters wide. These panels sit on parallel steel rails embedded into the stadium's upper structure. When the roof opens, the panels don't rise into the sky. They slide sideways along those rails and stack on top of each other, like 2 oversized steel playing cards being shuffled into a single pile. The rails themselves are engineering achievements in their own right. They're built to support loads nearly 40 times heavier than a standard railway track, while maintaining alignment tolerances measured in single-digit millimeters across their entire length. A deviation larger than 3 millimeters anywhere along that track can jam a panel mid-operation. Here's the part that surprises engineers outside the industry. There's no single giant engine driving this movement, not one massive motor. not a central power unit the size of a building. Instead, engineers distribute the workload across dozens of smaller motors, sometimes as many as 40 individual drive units per roof panel, each rated between 50 and 75 kilowatts. Individually, each motor is unremarkable, a standard industrial unit, but combined and synchronized, they generate enough coordinated force to accelerate thousands of tons from a standing start without a single visible jolt to the structure. The key word is synchronized. If even one motor falls behind by a fraction of a second, the panel experiences uneven force across its width. At this scale, uneven force becomes torque, and torque at 11,000 tons can twist steel beams the way you'd wring out a wet towel. To prevent this, computer control systems recalibrate motor speed up to 1,000 times during a single roof operation. One correction every second, throughout the entire movement, invisible from every seat in the stadium. This synchronization technology was borrowed directly from naval engineering, specifically from systems keeping large military vessels stable at sea, where multiple propulsion engines must coordinate perfectly to prevent a 300-meter ship from rolling dangerously in rough water. Surprising fact number 1. The panels move at speeds under 2 miles per hour throughout the entire operation. That's not a technical limitation. It's a deliberate engineering choice. Slower movement gives the control system more time to detect and correct deviations before they escalate into something dangerous. Surprising fact number 2. Wind sensors embedded directly into the roof structure can detect gust changes as small as 2 miles per hour, triggering automatic recalculations of safety thresholds continuously throughout operation. The roof reads the weather in real time and adjusts its own behavior accordingly, without any human input required. Surprising fact number 3. Some roofs are engineered to maintain full structural stability in any position, fully open, fully closed, or any point in between under hurricane-force wind conditions. Most buildings are engineered for stability in a single fixed state. These roofs must survive every possible configuration simultaneously, because a storm can arrive while the panels are still mid-motion. Each panel runs on industrial bogies, wheeled mechanisms descended directly from freight train undercarriages, redesigned to distribute thousands of tons across multiple contact points simultaneously. Without this load distribution, a single bogie would punch through its own rail within minutes of first operation. What looks from inside the stadium like a smooth, almost silent sliding motion is actually the result of 40 synchronized motors, 1,000 microcorrections per second, and continuous real-time weather monitoring, all happening invisibly, 60 meters above your seat. Now here's where the engineering story gets genuinely dangerous, because real-world conditions don't follow engineering assumptions, and the industry learned that the hard way. In January 2010, the roof at Cowboys Stadium in Arlington, Texas, became the center of national attention during a winter ice storm. Overnight temperatures dropped far faster than forecast models predicted. Massive ice sheets formed across the closed roof panels, with individual chunks growing to weights exceeding 45 kilograms. Roughly the weight of a large Labrador retriever, frozen solid, adhered to a near-vertical steel surface 60 meters above ground. When temperatures rose the following morning, those ice chunks didn't melt gradually. They broke free suddenly and fell. 6 workers were injured. Several required hospital treatment. That single incident triggered a complete industry-wide review of cold weather protocols across every retractable roof system in operation worldwide. Engineers discovered that ice accumulation creates a problem fundamentally different from wind or structural load. Because it's invisible from the control room, forms unevenly across the surface, and releases with zero warning. A roof that passes every wind load calculation can still become catastrophically dangerous under 100 tons of unevenly distributed ice. 100 tons of ice. That's the equivalent of roughly 65 mid-size passenger cars, piled unevenly across a single roof panel, with nobody able to see it forming. Snow creates similar problems through a different mechanism. Heavy snowfall doesn't just add weight, it adds weight asymmetrically. One side of a roof can accumulate 3 times the snow load of the other depending on wind direction during the storm. Japan took this problem to an extreme. The Sapporo Dome sits in one of Japan's heaviest snowfall regions, receiving annual snow accumulations exceeding 6 meters, enough to bury a 2-story house completely up to its roofline. But snow wasn't the only challenge engineers faced in Sapporo. The city sits in an earthquake-prone zone where ground shifts of several centimeters can occur within seconds and without warning. Standard rigid roof construction would crack catastrophically under that kind of sudden lateral displacement. Rigid connections between a 14,000-ton moving structure and a stadium foundation, suddenly shifting sideways by 5 centimeters, would transfer destructive shear forces throughout the entire system simultaneously. Engineers installed flexible joint systems throughout the Sapporo roof structure, connection points specifically designed to absorb and dissipate seismic energy rather than resist it. The engineering principle is identical to base isolation systems used in earthquake-resistant skyscrapers, where the building is designed to move gently with the ground rather than fight against it. Thermal expansion adds yet another invisible layer of complexity. Steel expands and contracts with temperature changes. Across a 200-meter roof panel, a temperature swing of just 20 degrees Fahrenheit produces linear expansion of approximately 15 millimeters, larger than the combined width of 2 stacked coins, across what's supposed to be a precisely aligned, millimeter-accurate rail system. If engineers don't account for that daily expansion cycle, panels gradually jam against each other. Rails develop stress fractures under unexpected compression. To prevent this, expansion gaps are deliberately built into every connection point in the rail system. The same engineering principle used in long suspension bridge decks, where thermal breathing gaps allow the structure to expand and contract daily without buckling. Perhaps the most overlooked challenge is operating all these systems together, simultaneously, in real time, with tens of thousands of people sitting directly beneath them. At AT&T Stadium in Texas, the seated capacity exceeds 80,000 fans. That's 80,000 people positioned under a moving 11,000-ton structure, trusting engineering systems most of them don't know exist. Every backup system, redundant motor arrays, emergency generator banks producing over 2 megawatts of standby power, manual override controls accessible from multiple independent locations, exists specifically because engineers had to assume complete primary system failure and design past it. 2 megawatts of backup power. That's enough electricity to simultaneously power roughly 16 average American homes, dedicated entirely to one purpose: making sure this roof can always finish moving, no matter what fails first. Engineers run full emergency drills, simulating total primary power failure during active roof movement. Not occasionally, but on a regular scheduled basis. Because stopping an 11,000-ton structure halfway through its travel introduces its own set of structural risks, sometimes greater than the failure that triggered the stop in the first place. Weather forecasting teams now monitor atmospheric conditions up to 6 hours before any scheduled roof operation. Wind speed trends, ice formation risk, temperature trajectory, precipitation timing. The decision to move a structure this size involves multiple specialists and is never made in under an hour. Control rooms for modern retractable roofs look less like stadium operations centers and more like the command deck of a naval vessel. Banks of monitors showing real-time motor, load data, rail alignment sensors, wind readings from a dozen separate points across the structure, and live camera feeds of every major mechanical component. 5 engineers can be watching a single roof operation simultaneously, each monitoring a different system, each with independent authority to abort. Every protocol in use today exists because something, somewhere, already went wrong at least once before it was written into the manual. Now let's get into the facts most people sitting in those seats never hear. First, some stadium roofs generate enough vibration during movement to register on seismic monitoring stations located up to a kilometer away. The reading mimics a small, localized earthquake, measuring approximately magnitude 1 on the Richter scale. When seismologists first detected these readings near a major stadium in the early 2000s, their initial assumption was a minor geological fault slip. It was the roof opening for a Tuesday night game. Second, if you disassembled the complete steel framework of one large retractable roof and laid every single beam end to end in a straight line, that line would stretch over 6 kilometers, longer than 60 consecutive football fields, long enough that you couldn't see the far end from the starting point on a clear day. Third, closed-roof stadiums regularly record internal temperatures up to 10 degrees Fahrenheit warmer than outside conditions, even with no active heating system running. Steel and fabric panels absorb solar radiation differently than open air, creating localized greenhouse effects that engineers must actively counteract with dedicated climate control systems, consuming over 5 megawatts of power on a warm game day. 5 megawatts, enough electricity to power a town of 4,000 households, used solely to manage the temperature inside one building. Fourth, the longest continuous rail track on a single retractable roof system spans over 300 meters, longer than 3 American football fields placed end to end, machined to alignment tolerances of less than 2 millimeters across its entire length. Achieving that tolerance on a structure assembled outdoors, across multiple construction seasons, in variable temperatures, is considered by structural engineers to be among the most demanding precision alignment challenges in modern large-scale construction. Fifth, and here's the controversial part stadium owners rarely advertise openly. Some retractable roof systems cost more per square meter to construct than the most expensive residential real estate on the planet. Annual maintenance budgets for large systems regularly exceed $5 million per year. Over a 30-year stadium lifespan, that's $150 million in maintenance costs alone, entirely separate from the original $300 to $500 million construction investment. Critics argue that money could fund youth sports infrastructure across entire cities, meaningful reductions in ticket prices, or community development programs that benefit millions of people who will never attend a single game inside that stadium. Supporters counter with a single number. One canceled playoff game due to bad weather can cost a franchise over $50 million in lost broadcast rights payments, ticket refunds, and sponsorship contract penalties. At that rate, even a $500 million roof investment pays for itself within 10 years of weather-related revenue protection alone. The debate has no clean resolution. Both arguments are financially sound, but engineers on both sides agree on one uncomfortable truth. Once a retractable roof is built, it must perform flawlessly every single time it operates for 30 years, through ice storms, earthquakes, power failures, and hurricane-force winds, because the alternative is never acceptable when 80,000 people are sitting underneath it. What nobody on either side disputes is the raw engineering achievement itself. Moving a structure heavier than the Eiffel Tower, with millimeter precision, above 80,000 people, in under 20 minutes, without a single person in those seats feeling a vibration, that's not just construction. That's one of the most demanding engineering problems solved in the modern era, hiding in plain sight above sporting events most fans attend without a second thought. So here's what you actually witnessed today, broken down to its simplest form. An 11,000-ton structure, 40 synchronized motors, 1,000 microcorrections per second, wind sensors reading atmospheric changes of 2 miles per hour in real time, backup generators producing 2 megawatts on instant standby, rail tracks machined to 2 millimeter tolerances across 300 meters, all of it compressed into 20 minutes of movement so smooth, so quiet, that 50,000 people sitting directly beneath it never felt a thing. This technology started with a fixed dome in Houston in 1965, a roof that couldn't move at all, built just to keep the rain out of a baseball game. 6 decades later, engineers are moving structures heavier than small bridges above crowds of 80,000 people, in less time than it takes to watch a single episode of television. The gap between those 2 points, a fixed concrete dome and an 11,000-ton sliding steel structure, represents 60 years of failure, refinement, near misses, ice storms, earthquake engineering, and thermal expansion calculations that most people will never know existed. Every retractable roof operating today is a compressed archive of every problem that ever broke a previous version. Every expansion gap, every redundant motor, every seismic joint, every weather sensor. Each one exists because an engineer somewhere looked at what failed and decided it would never fail that way again. Here's the question worth sitting with. If engineers can move something this heavy, this precisely, above this many people simultaneously, what does that tell us about the limits we assume exist in every other massive structure around us? Maybe the real story here isn't about steel, or motors, or wind sensors, or 300-meter precision rail tracks. Maybe it's about what happens when engineers simply refuse to accept that something this heavy cannot be made to move safely above human beings. If this changed how you see the world, hit subscribe. We uncover the truth behind things you thought you already knew. Right now, somewhere in the world, a stadium roof is sliding open above a crowd that has absolutely no idea what's happening directly over their heads. 40 motors, 11,000 tons, 1,000 corrections per second, 20 minutes. They never felt a thing.